Computers are completely stupid. Machine language, the internet know nothing about time. Nothing, and that's why it works. Before, they predicted there would be a plane crash every week. The pilot doesn't crash the plane anymore. Since the A320, which was the first one, it has a video game joystick and it talks to the computer. Testing isn't enough to prove it.
Hello everyone, welcome to this new episode. Today we welcome Gérard Berry, with whom we will be able to talk about computer science, technology, and try to understand how these innovations have become established in our societies. Hello Gérard Berry, hello, we are very happy to have you with us on the set. For those unfamiliar with you, can you introduce yourself?
Yes, I've been a researcher since I was very young, so I followed a fairly standard academic path, attending École Polytechnique. After that, I joined the Corps des Mines and immediately started doing research. And then I met a lot of people around the world. It was really the beginning of major research in computer science. I met some fantastic people around the world. And then I worked on we didn't have a computer in France, that's important to know. It was forbidden for researchers. I'm a computer science researcher. And so we did a lot of things in theory, some really great things with my friends.
You started studying computer science, working in computer science at a time when there were no computers in France?
Well, I was lucky because at Polytechnique, we were on Montagne Sainte-Geneviève in the 5th arrondissement, but we were cloistered because we were in the military. And someone told me that there was a strange computer in a room that nobody used. Well, we had nothing to do, so there was a bit of teaching, but honestly, I found it a bit simple. So I went to the machine, and that's when I made the discovery that changed everything for me. A computer never makes mistakes. It's exactly the opposite of a human being. Zero intuition, never any mistakes. So how do we get this thing to work? So it was a very special computer at the time. And then I met by chance, I had a motto, which is you never know when you'll get lucky. That's my number one motto. And I met extraordinary people completely by chance. A very great researcher whom I worked with a lot in the United States, where I was on a trip paid for by the mines, by the way. I was walking around a university, but I had broken my leg, not my knee. I didn't break it, but seriously, I had broken my knee. And you don't go to a doctor in the United States. And so I arrive in Palo Alto in Silicon Valley, which at the time didn't exist. It was Stanford, not Silicon Valley. And then I just had a phone number. I called the gentleman who says, "Oh, you can't walk anymore." Well, listen, if you want, I'll take you. I'll put you up for 15 days in a student hotel nearby, and then I'll take you to my workplace. And this gentleman was the first to have done rigorous mathematical proofs on a computer. This is a subject that is represented at the Collège de France by Xavier Leroy, who is now a professor and who is extraordinary in that area. There you go. So back then, there weren't many of us. So it was very easy to meet people at conferences. There was little competition. We were almost not allowed to write papers during our PhD. So now I think research has become crazy. It's a terrible competition with a very large number of flawed papers. You can't even know. They're not even read by the reviewers. So it's fine, because obviously it's very big now.
Yeah. So what was computing like back then? Because I guess it had nothing to do with what we see today.
Actually, it did. It had a lot to do with it, because the problems we faced were exactly the same as today, except for big data. That didn't exist. But when it came to programs, the problems were exactly the same, and people still weren't aware of them. The thing is, making a program is exactly that. The machine never makes mistakes, but humans make a lot of them. How can we tell if a program works as intended? Well, that's, for example, we made planes fly or things like that. We're not joking. You don't see, like in phone apps, every 3 days, something like bug fixes or interface improvements. That's written in all the apps the same way. Well, we're not allowed to do that. So you have to do it right from the start. And so I started really early with people like Dana Scott, who was a great mathematician, a pre-Turing, Robin Miner, who was a pre-Turing, and a rather extraordinary theoretical computer scientist and a practitioner as well, by the way. And I started with them on this problem. How can we make programming rigorous? And that people didn't impose on themselves because they would create languages and then afterwards they would think about it. For example, the most well-known language is C. Well, C, in the current C standard, there are 120 cases, things you can write that are undefined. We don't know what they mean. Oh, really? Well, now we've managed to eliminate a lot of cases to make a very simple C, because that's what came before assembly language. Assembly language, you can't learn it. It's not possible for a person to program in assembly now. It's impossible because it's very complicated. And it's not just that it's complicated, it's that there are extremely tricky things about timing. So we generate it from a language like C. And so we need to create languages where when you write a statement, you can know what it means. That's still not the case today. But when you have a safety critical system, critical for safety, not security, but robustness, well, you have to provide mathematical proofs. And with our tools, there were always mathematical proofs for a program. How can you prove that a program doesn't do something? Well, you can't say everything. Well, you prove what you're asked to, but you can't just say it works. That sentence doesn't make sense. Compared to what? There you go. And that started very early. That is to say, I was at a conference. I was just a beginner student at a conference in Amsterdam where Dana Scott was speaking, who was explaining his theory of information and programming, and who, for example, gave one of the great proof systems in the world, which was done in France, first in Nancy, then at the École Normale Supérieure by Patrick Couzeau, and then many other things. So it was an extraordinary time. Fortunately, we didn't have much at stake with computers because the friends we had spent all their time programming. You need to know how to program. We spent some time on it since we went abroad for that. But you have to do and think at the same time. And that's not typical of computer scientists in general. They do things, then they think it works.
So to explain a little to people, to program, we use a language, a programming language, which is meant to code instructions. For the machine, how could we define it then?
A language is an intermediary between human thought and the stupidity of computers. That is, computers are completely stupid. What can machine language do? It can take something from somewhere and put it somewhere else. That's operation number one. Perform an addition. So since you have to perform additions for operation number one, the machine basically spends its time performing additions. And then it's things like that. But expressing programs with things like that, it had to be done at the beginning. It's insanely hard because it's annoying. Well, there's a French word for that, but I won't say it. You know what I mean? It's annoying. And so little by little, we're getting closer to humans. For example, we write x plus 1, or x equals x plus 1, which is better theoretically, because x is never equal to 1. But anyway, why do we write x equals x plus 1 in C? Because back then, computers were very small. Even a colon took up too much space. Oh yeah, you have to remember there were limitations. My first compiler for our STRL language, I developed it on a machine that had a gigantic hard drive, 10 megabytes. Well, yes, I'm the one who has a photo.
Yeah, well,
so we didn't have the same working conditions. And that's also why we had to be very precise, very rigorous. That's it. And it was a great opportunity because we immediately had the feeling that the machine was uncooperative. People no longer feel that way because there are now so many tools. But one thing that's still true is that when there are bugs, people think that's normal. I never thought that was normal. But it's very hard to program without bugs.
So, to get back to programming languages, we talked about several languages like C and assembly code. There are different types of languages that are more or less complicated. What distinguishes them?
Well, there are thousands of languages. There are different types. I focus on it in particular because I've done a lot of work on time-related issues. Obviously, when you're making airplanes fly or working on circuits or things like that, time is central. But time already is divided into three. People don't usually know that. So the first one is sequential programming. That means a machine does conceptually, physically it's not true, but conceptually, one instruction at a time. That's what we learn at school. That's pretty much what most people know. All right, that's called sequential programming. It was invented in 1936, maybe even earlier, because the word algorithm is not Greek at all, but it comes from the name Al-Khwarizmi, a Persian mathematician who wrote in Arabic around 900 or 950 AD, and he had brought Arabic numerals from India. So it's once, the Indians had really known number theory forever, but they had imported it because they found it was much better than what they had at the time, which were very complicated things. Thinking in Roman numerals, multiplying in Roman numerals, that's a sport in itself. So he had invented algorithms, but he wasn't the one who gave them their name. The word algorithm in French dates back to 1215. It's not exactly recent. And it doesn't have a Y, it has an I. It's Al-Khwarizmi. And so he also invented, he's the one who came up with a solution to the quadratic equation, which all children learn. They're never told that it was him. And then he's the one who invented algebra. Algebra is included in the title of one of his treatises. Computer science goes back a long way. And then the idea of instruction by instruction programming comes from Turing, 1936, who was truly an extraordinary genius because he did many other things as well. And also Church, who created a language called lambda calculus. I won't go into details, but it's a completely opposite kind of language. It's an extraordinarily powerful language, which is the foundation of all modern languages, even JavaScript. And I worked a lot on lambda calculus. It's a truly fascinating language. So there you go, those are sequential languages. Then there are asynchronous languages. That means it came later since you needed multiple machines to communicate. Or even in operating systems, a program executed by the same machine. And what does that mean? It means they talk to each other, but they cooperate. All right, now it will be out computing. Things like that are everywhere. So the problem is, for example, when we do, so this is a bit for people who know a little about computers. There's something very well known called make. Make means when you have a program with lots of files, when you change one, you specify what needs to be changed and what doesn't. It's very easy, it's well designed. And that's what we say. But if we put this on several machines, we have a big problem because things must be done in order. We change this first, then that. If they're not on the same machine, you must follow this order. So you have to do what's called a synchronization. You have to find a way to avoid mix-ups between the machines. And the machines, they don't have the exact time. The problem with the time, that's what's obsessing me right now. They don't have the exact time. So we can't decide who did something first by looking at their clocks. So we need what we call protocols. Or when we communicate by phone, you have to know that people don't realize it, but the phone is now just the internet. A cell phone is just an internet device, that's all. Well, that's very complicated because the internet made a fundamental decision, which is not to know time. The internet knows nothing about time. Nothing. That's how it works. The old telephone networks, they did know about time. were organized, divided into time slices, etc. The lines were split into pieces. Well, the modern electronic networks, they were split into pieces and everything. But to know about time itself, you need a map of the network. Internet, because of the original design choice, will never have a map. Well, yes, there are. So on Twitch, I don't know how many tens of billions of objects, because objects are the majority, billions of objects that interact like that. So there you go. So, well, on the internet, synchronizing things is absolutely not simple. And there are a few people in the world who have done what it takes. But here, it's definitely not something for beginners. So in computer science, we never talk about time. More precisely, in classical computer science, time is a tax. It's what you have to pay for computation. One where we talk about time, but without actually talking about time. We talk about the synchronization of things that each have their own time, completely different, not at all the same people, not at all the same theories, completely different backgrounds. And the third is that programs must respect time. They must know it and respect it. And that's what we now call computerized objects that do things in real life, not just provide interfaces to machines. By the way, in a Raphael, the interface to machines is obviously serious. But there you go, they do things that depend on timing. That's what I did. It originated entirely in France. 3 labs in France invented this independently. I was the first one historically, but that's not necessarily very important, with 3 methods that are a bit different and very complementary. And it was known for quite a long time, but only among the industry professionals who needed it. And now it's very well known. And there you go. So it's computing with time, totally different. Totally different.
All right, so what are the main differences then in the design?
So in the design, it's when we say we're going to do things in parallel, in asynchronous computing. Since they're never at the same time, you have to know how to synchronize them. You have to know how to pass information at the right time, wait for it, but not get stuck waiting. All right? And that creates incredibly sneaky bugs. So I'll tell you about 2 of them quickly. Because I wrote a book called The Hyperpower of Computing, where I explain it in detail. It's Pathfinder and Spirit.
All right.
The 2 super famous Martian robots. All right, Pathfinder lands on Mars. During landing, they shut down the computer, which is normal. It lands on Mars, and the first thing it does is restart the computer. In particular, because we need battery power. Because if it doesn't have a battery, the robot can't do anything. So that's it. So it reboots, as we say. It starts up. So they're watching this from Earth. Well, they're watching this with an 8-minute transmission delay. And it pulls back, and then all of a sudden, nothing. Nothing. The computer that doesn't do anything anymore. That's a bug in asynchronous computing. It's where different tasks are talking to each other. And there were several tasks in the same machine, but it's not a big deal. It's the same and nothing else. Okay. There was another processor beside it that would reboot it when it detected inactivity. Because there could be cosmic rays. Okay, it reboots, and then after about the same amount of time, nothing happens again. So there were batteries, it wasn't charging. And it kept rebooting them, so it was headed for certain death. And then back on Earth, people were working. They didn't understand. And then they finally understood, because they had really tested. But testing is not enough, you have to prove it. And they had understood that there were 2 tasks that were in deadlock. That is to say, in a fatal embrace. It was the communication task with Earth and the weather task. Presumably, few tasks were running in parallel in the system. And simply at one point, they both needed resources. I'm not saying which one. And simply, they were in a state where each was waiting for the other to give it to them. I compare this to 2 twin girls in my family. One has a ruler and the other has the pencil. Then they wait for the other to give it to them so they don't sign. And then they ended up finding out that it was a bit in the operating system, which is called the priority inheritance bit. It's managed with priorities and things like that. It's called the priority inheritance bit. Well, I'm not going to tell you what it is. There was a bit that had been set to 0, probably so that it would compute faster. And bam. So they noticed it a little before the batteries died. And they sent a message saying to set that bit back to 1, because fortunately for the technicians, they had left the operating system in debug mode so they could do that. And they set the bit back to 1, just 1 bit. And then Pathfinder worked for. So that's an asynchronous bug. That's really 2 tasks waiting for each other and not doing anything anymore. That doesn't exist in traditional programs. So Spirit is an even more extreme case. The big robot that was supposed to live only a short time but ended up living for years and years, it was killed not long ago. It was abandoned not long ago. Well, it was kind of the same here. Do you remember when I said one had the pencil and the other had the ruler? Well, then little Manon arrived and the other 2 decided to pass the ruler and the pencil to her, so she's the boss. But little Manon, she's afraid to grab either one. So that's what we call starvation. There you go. And that's exactly what was happening. Yeah, it was a totally stupid thing. There was an old Microsoft routine that handled the flash cards because there was flash memory. And obviously you always need solid and flash memory. And it was reloading the flash memory. And the flash memory was only twice as big as the regular memory. Well, I'm not telling everything. And because of an absolutely stupid bug in an old Microsoft routine, well, I can tell you, for those who know, when they deallocated, they were used a lot during the flight because they took lots of measurements. And when they deallocated a slot that had been allocated for certain data in the flash memory and it was no longer needed, they removed it. But they wouldn't send the thing that said where they had put it. So that's what we call a descriptor. And the descriptors had filled up more of the memory. So when they reload, the operating system says the memory is full. And he says, so I'll wait. That's starvation. And there the engineers worked like crazy. Those are really tough bugs. They worked like crazy. And they gave up, except for one who stayed. And in the early morning, he found the bug. And it took a very long time to fix because they had to do a complete remote reset of the machine, making sure everything was going well at each step with 15 minutes of waiting each time. And then Spirit started up again. So it's the tiny details that can kill.
That's
Computer science.
there. It can literally be a 1 or a 0, can completely block a machine.
Exactly.
But then, how can we make these machines more reliable, especially since our systems are becoming more and more complex and interconnected? How can we approach code? How can we program robustly in the world we live in?
The first thing is to stop believing that we're smart. That's fundamental. Otherwise, it's over. Someone who thinks he knows how to do it, you have to give up on him. It's still better to have people who know what they're doing than those who don't. But bugs are sneaky. So look at the whole 737 thing. I don't know exactly what the bug is, but apparently. So first of all, you have to be completely serious. But if you think testing is enough, the answer is no. No. Tests only tell you that what you tested worked. What we want to do is better than that. But that's not always possible. It's proof that tells us what can't be done. There aren't things that don't work. And that's the mathematical proof. Only logic allows us to do that. And I worked a lot in that area. And now there are still things we can do. For example, Xavier Leroy, who is now a professor at the college, made a high-quality C compiler. That means it produces pretty good code, but it's usable for cases where you don't optimize like crazy, because when you optimize like crazy, you're sure it's buggy. Sure, at the moment, that's absolutely clear. But he still uses it quite a lot, and it is fully proven to be mathematically correct, which proves that the language he writes in is completely mathematical. It's called Camel. It's a French programming language. And there you go, you need all these steps. But we can't afford that for ordinary computing. Actually, when we introduce bugs, people don't care. They're used to it. They think that's just how it is. Well, no. And so in synchronous computing, oh yes, because here there's an extra feature, it's parallel. We do things in parallel, but without any temporal relationship. And so that's what we call non-deterministic. That is, we run programs, and if we run them twice, the same thing won't happen. That's normal. A classical program, if you run it 1,000 times, it always does the same thing. Here it doesn't. And there can be a number of situations. We can't test them all, because the number of possible situations can easily be greater than the number of particles in the universe. If we want it to work, we have to prove it. For example, distributed database protocols. Well, no one can just assume they work like that. And so those are things that have been proven with extremely clever systems. That's a type of computer science most people aren't aware of. It's a very mathematical kind of computer science. The absence of bugs can be proven. Not always, and it's not worth doing all the time. An operating system at the present time is not proven.
D'accord.
I don't know. But when it crashes, people think it's normal. In airplanes, that's not normal. So it's still important to know that with the quality we have now and the tools, which are not at all the tools known to the public, there are no more plane accidents.
Very few.
It used to be expected that a plane would crash each week. Anyway, so that has changed, and it's largely because of electronics, but it has also changed the pilot's job. The pilot no longer flies the plane. Even since the A320, which was the first, the pilot has a video game joystick and he talks to the computer. And he has no physical contact with the plane. Thank you. It works, but you need to know how.
Earlier, we talked about the fact that the program could take time into account. How can a machine integrate the notion of time, of temporality, into the way it operates?
That was the major work done in France, which is now considered classic. Because I forgot to mention, the company Estoril Technologies had developed new software combining two French synchronous languages. Lustre, which had already done a lot for Airbus because it was really their programming platform, and it's made in Grenoble. And then Estoril, the one we made in Sophia Antipolis. He found a clever way to mix them, which engineers like a lot. It's graphical. It's very much in the engineering style, but it's completely mathematical, which is perfectly well defined, which is certified. That is to say, the authorities, global certification authorities, have considered that it has the same reliability as all the aircraft parts subject to that process, or even higher in terms of certification. And that's where Boeing made a fundamental mistake. He managed to convince the Federal Aviation Agency that it was enough to just listen to them for certification, that they didn't need to take care of it themselves. And obviously what they did was nonsense. So that's how they do it elsewhere. And now that's something that's used on a very large scale. And the company had been bought by Americans. It didn't interest the French, nor the Germans, nor the Europeans. No one. There is no one. And it was bought by the Americans. It was bought again in January 2025 for $35 billion. Well, it wasn't just the technology. He also had, because now they're doing what we call digital twins. That is, these are things that are, for example, in an airplane. It's a virtual airplane that flies at the same time as the real airplane with the same data doing its calculations. And we try out new programs like that. We try improvements or we find errors and so on. With a real airplane flying, then there's a digital airplane that tries to understand if the real airplane is doing the right things. So that's a big topic. So how do we do it? First, the language has nothing to do with the others. For example, SRL can mean, for example, I'll give you a sentence, an instruction. Every morning you go to the stadium. And I mean, every morning you go to the stadium. Then to run. So what is it? You're going to do a running session by doing, let's say, 10 laps. And each lap, you start running slowly for 100 meters. After that, for 300 meters, you run at full speed. But with every step, you jump and you exhale. And then at the end, yes, you only do that for 4 laps, then for 10 laps, then at the end it's over and you have to come back the next day. So how do we program that? Well, with a traditional language, it's completely impossible. It's a nightmare. Here we say it's simple. What are the units of time? There's the morning. That's a unit of time. There's the hour, the second. That's the same thing. No, not the morning. That changes every day. Then there's the meter. But it's the same. The second and the meter, it's the same. We go through seconds and meters. So waiting 3 meters or waiting 3 seconds, it's the same. And then there are actions like jumps. And then we ask ourselves a question. There's the part where we jump, we breathe out. It's a bit dangerous. So you have to monitor the heart. So how do we monitor the heart? There are 2 methods. Either we check within 2 seconds if there's a heartbeat. Because heartbeats and seconds are the same. They're units of time. And the second is nothing special anymore. And then, or we check if there's at least 1 second or more than 2 seconds between 2 heartbeats. In one case, we place seconds around heartbeats. In the other, we reverse it. Both make sense. There's no difference in the language. The program is written like this. Every morning it can run an infinite loop. For 4 laps, start by running slowly for 100 meters. These are instructions to say that. And that has nothing to do with regular language. And that's how we used to make circuits. And descriptions related to the language of the circuit that are completely strange. And on top of that, there's a compilation technique that's extremely, it took us over 10 years to find the right approach. And then we beat humans. Always. We used to beat humans every time, but now this technique has been somewhat abandoned. It's not a big deal because this industry is too dependent on too many things. We used to beat humans all the time. Okay. Well, that's it. So it's completely different from the rest.
Okay, I saw you helped create a programming language. And so that's the characteristic of this language that you created.
Yes. And there are 2 styles to do this. There's the style of his language, which is called an imperative style. It's a sequence of commands. There's also the declarative style. It's more declarative. It's more for things that hum along but are very complicated. That means it doesn't really change modes much. We, on the other hand, are constantly switching modes in what we do. We never stop. For example, on a plane, there's a screen that's not very big, and then there's a screen over there. In a Rafale, for example, the pilot has 17 buttons on the joystick. Why? Because he can't move his arms. So he has 17 buttons, and what the plane does depends. You don't do the same thing if you're going down or going up. When descending, you typically don't use the radars if you turn. When you're going up, yes. So we don't do the same thing. The behavior constantly changes. And Dassault was our first major user. Or when we run tests, that's a big program that we've actually proven correct in many ways. When we run tests, there are flight tests and ground tests. Well, it's managed by a single program, but they had a question, which was, during ground tests, if we do that in flight, there won't be a plane anymore. At the time, they only had one more. So you see, they took things seriously. And well, the techniques to do that are complex. I explain a bit about it in this book, but it's really tough stuff. But well, it's not visible to the user. He doesn't need to know that, but he can.
So that allows me to make the perfect transition to your book, so Le Temps Autrement. I find the title interesting because given the title, one would have expected a physicist's work. So what is this book about?
There are books by physicists that talk about time. There are tons of them, as many as you want. They're still pretty similar to each other. And I've always been fascinated by the notion of time. And here we're talking about everything except physics. That is, we're talking about the history of time measurement. Perception first, the perception of time, because the perception of time is extremely imprecise. We don't have a sense of time, none at all, except for music. That's a great mystery to me. All civilizations. It's roughly the rhythm of walking or the heartbeat. Music always falls in that range. We're very strict about time in music. The rest, I'm talking, for example, about vocabulary. I'm also a pataphysician. I'm a regent of deformatics at the College of Pataphysics. Computer science is the science of information. Deformatics is the opposite. But it's not the science of disinformation. It's the science of the deformable. And so time is eminently deformable. And the history of time measurement is extraordinary. It is unknown in France for a simple reason. It was solved by the English. The English, they had boats. They couldn't go by land because Louis XV forbade them, and they had boats. But a boat needs to know the exact time to know where it is. All right? I'm not talking to you about the details. And so there was a great shipwreck of the English admiral's fleet as well. They thought they were in Brest. They were at the Scilly Isles. It's full of reefs there. All right, and this story is fantastic. And it was solved by a carpenter. A watchmaker named John Harrison, who made an extremely precise watch and released it in 1962. But the story is absolutely amazing, but this one isn't mine, because I'm borrowing it from a fabulous book called Longitude. And it's completely unknown in France, but it's true that there was a Bureau of Longitudes at the Academy of Sciences, well, at the Institute. And when it was created, its founder said, we made a huge mistake in believing that England would be a secondary power because now it's the #1 power since it has conquered the seas. It was purely a matter of keeping time. All right. And then after that, now time is measured. So physicists, there's almost only one emission, I would say, in physics now. In that kind of physics, they make fantastic clocks. There are some extremely talented people. Currently, the best clocks drift by about 1 to 10 seconds over the age of the universe. So that's not the problem. So then there's a chapter that tells that story from ancient times with all its wonders up to now. Then there was the issue of how you distribute time to people. We're used to it now. We have wristwatches, but wristwatches for everyone have only been around since the 1950s. And now we have GPS. Well, I've noticed that nobody knows what GPS is, except for the people who know, but there are very few of them. Well, GPS is very simple. It's atomic clocks that synchronize in the satellites. There's a general relativity to do that, but it's pretty fantastic. And they send the time to within 10 billionths of a second. That's all. That's all it does. And no, it also tells where it is. That's it. Well, that's how it is. So nobody knows what it is. But the GPS, for 30 euros, you can buy a GPS jammer. It's forbidden. It's punishable by jail, but it's freely available. and you can pay to jam it. And then nobody has GPS. It depends on your jammer, but it can go pretty far. And for example, there's a map of GPS jamming every day with the war in Ukraine. Well, Finland, Poland, there is more than 10% of the time when GPS is jammed. And sometimes it's completely jammed. And that causes huge problems, even in France. For 2 months, planes landed visually in Marseille. Fortunately, it's in Marseille. There aren't too many clouds. And why? Because there was a GPS jammer in a tanker truck. So it's serious. And now the main target in a war is the GPS. We've been trying to explain that to French leaders for years. They haven't had any success. For example, the Americans, they have a territory that's a bit far away. Europe is small, but the Americans have no backup way to get the time. The Chinese, they have a network of fiber optics and local transmitters. They transmit time with nanosecond precision that way. Well, impossible, but politicians don't understand that. Anyway, there's not a single politician who has spent even an hour studying science, so it's serious. Nobody knows about it.
If I understand correctly, you can destabilize an entire country and cut off a large part of its navigation systems simply by preventing them from being able to synchronize computers with respect to time.
Yes. In Ukraine, since it's jammed everywhere, the drones pull fiber optic cables behind them.
D'accord.
All right, yes, to get the time. Yes.
Okay, super interesting.
And so, well, yes, that's something else entirely.
And so, in this book, that's one of the points you develop. So, what else do you discuss in this book?
Some adorable stories. For example, did you know that in France, in train stations, there used to be 3 clocks in each station? Until 1920 or even later than that, there were 3 clocks. And it was really funny. First of all, each town had its own time, solar time, until not very long ago. And so there was the town clock, but you don't schedule trains based on each town's clock. So train schedules in France were set in Paris according to the Paris clock. So there was the local clock and the Paris clock. And on the platforms, you didn't see those two. There was a third one that showed the time in Rouen. Why the time in Rouen? Well, it depended. In France, it was Rouen time. In Belgium, it was Brussels time. But Rouen time, because it was 5 minutes ahead of Paris time. And that allowed people to arrive late at the station. Yes, because getting to the station was never guaranteed. So there you go. There were 3 separate times, and it stayed that way until not so long ago. And world time, it was Greenwich Mean Time, except in France. Because in France, they eventually adopted Greenwich Mean Time, but we still didn't have to call it that. So we called it Paris time minus 9 minutes and 20 seconds. So as not to say Greenwich. So the history of time is extraordinary. And in England, they had no way to distribute time because the clocks were all over the place, in the street. Well, there was someone who had worked at the Greenwich Observatory, which was closed to the public, and he had the right to go there, and he went there. He had a very beautiful watch, very precise. He went there. He set his watch very precisely, and then he made the rounds of his clients. He sold accurate time. That lasted until 1940. His daughter was on the promenade, lady time. In 1940, they installed the talking clock, and that was it. So there are stories like that. There are plenty of them. There are plenty of them.
It's true that today timekeeping feels pretty natural now because with satellites, we always have synchronized phones. But it wasn't always like that. Before, we had to find ways to synchronize. How did we synchronize? We talked about clocks in train stations. How could we synchronize the different clocks in the stations before satellites?
Well, it's very difficult. So it was still approximate, but there were methods. For example, in Paris, there was a method that was very clever. It was even before we knew how to distribute electricity, it was pneumatic. So there was a steam engine on Soguin Island next to the factories that weren't there yet. There was a steam engine and a compressor. And there were pipes, which went all over Paris. And after that, it went to the suburbs on a very large scale. But it was all over Paris where there were clocks in the squares, in the monuments, and everywhere. And every minute it went poof. Suddenly all the clocks moved forward together. That worked very well. And that was, well, it was in the 1890s or even before, I think. Except that at one point, all the clocks in Paris stopped at exactly 10:53 p.m. because of a flood of the Seine that drowned the steam engine. So yes, it's always been a tough problem, much harder than measuring it. Distributing it was always difficult. Now we just ignore it. There was the not slow clock, 1936, Ernest Esteron, who was something absolutely fantastic. And that was used a lot. Now there's the Alois transmitter, which was the long wave transmitter from the era of long waves. Well, it broadcasts the time signal, but it's not nothing. It's 1 gigawatt during the day. A gigawatt. It distributes atomic time, by the way, and you can see it on transistor radios. There's a transmitter in Germany that there are a lot of devices, all the on-demand devices that go to Bosch, etc. It's synchronized from over there by radio waves, but they're very weak radio waves. And then they're single sites. In case of war, poof, poof, and that's it. Yeah, that's right. So there are 5G networks. They need a lot of synchronization. Synchronization is very, very, very useful. SNCF and EDF each have their own fiber network for time synchronization. Only for that. Well, it's also used for other things. But it's absolutely not simple.
You go into all these stories in your book. We'll add that to the description for anyone interested. But the thing is, computer science is an extremely important issue that we hear a little less about these days because artificial intelligence is getting a lot more attention and taking center stage. Is there a fundamental difference between artificial intelligence and computer science?
Classic, if I may say so. First of all, we're not talking about artificial intelligence. We're talking about just one aspect of artificial intelligence, which is generative AI, because it deals with language and everyone understands language. Artificial intelligence is a technique that is very different. It's completely different. I don't have any skills in it, for example, at all. And it can be reciprocal. It's a technique that calculates probabilities, but we don't know why it works. I had Yann Lecan at the Collège de France in 2016, at a time when the word wasn't known. There are 3 inventors of this technique, and all 3 of them won the Turing Award 2 years ago. It's Yann LeCun, Yoshua Bengio, and Jeff Hinton, 2 of whom are Canadians and have worked on this for more than 20 years. No one believed in that. But it actually works surprisingly well. For example, I use DeepL. I'm currently translating my book into English. I use DeepL. It's absolutely mind-blowing. But the questions are always the same for journalists. Is it going to be smarter than humans? But he has no definition of the word intelligence. You can answer yes, you can answer no, you can answer whatever you want. The articles are all the same. It's simple. Except that there are articles by people who know the subject. That's rare. We don't discuss the rest because we never cover 2 topics at once.
Yes.
In astronomy, we talk about cosmology, Hubble's discoveries, but there are many other things. No one talks about the planets of the solar system anymore. Yet there is a lot of research. So that's the media. I've never found that fascinating.
For those who say that computer science is a form of computational intelligence, can we really talk about intelligence when we're talking about computer science?
But the word doesn't have a definition. So yes, it depends. Looking up intelligence in French or English dictionaries gives you the same definition. In France, it's the ability to adapt to your environment. In that case, there are a lot of animals and plants that are intelligent. That means no one has ever managed to give a correct definition of the word, because there isn't one. We don't know what it means of things at the same time. So language didn't surprise me, because I have two children who are Franco-Finnish. Des enfants qui sont franco-finlandais. They learned both languages at the same time. No one ever taught them. It can't be that hard to learn a language. It's hard for adults, but at 3 years old, they don't even know they're learning it. They speak the others perfectly. That's not the issue. And even almost no adult manages to learn Finnish. They find it easier. So maybe difficulty isn't the problem. It's hard to find ways other than our own, and it's done now. So after that, there's a question of intuition, of truth. Intuition, we don't really know what it is. But these systems ne font que retell what they've been taught differently. They don't have any, for example, when you look at writers, the ideas they have, if the book is good, no one had those ideas before. And there, we don't know. We don't know. So I think we have to, it's very impressive what's happening. But I organized, well before anyone talked about it, conferences at the Collège de France on medical imaging. It's been at work for a long time, but nobody mentions medical imaging. There is. But machine translation didn't wait for the newspapers to talk about it. DeepL, I was using it in 2017. In 2017, nobody knew the word, because there had been a lot of failures before, methods that didn't work. This method works. We don't know why, but we don't know why it's not that different. And there's Stéphane Malat at the Collège de France, who is a great mathematician, a mathematician, but also in applied mathematics, who works on the subject. We know that it does probability calculations using stupid methods, but at full speed, because modern machines are like that. And it's very simple. It's very simple. Why does it work and how do you design it? It's an artist's job. It's not a job specifically for... How do you know if it works? At first, ChatGPT, I had it write my biography. I learned a lot of things. I was Richard Berry's brother, for example. I have two friends who found out they were dead. It's a shock.
That must feel weird.
Now it's still stronger, but we can't really judge. We don't know whether it still responds all that well. Now it answers more cautiously. Since the caveats are always the same, it doesn't really matter. C'est pas jugé.
The approach is quite different from traditional computing, which relies on accuracy and making sure programs work reliably.
Programs are simple. It's not the data that does the work. Data comes from nature. We use it to do other things. Whereas here, data is the material, really. Algorithms are generally simple. A neural network isn't complicated. But what comes out of it can be very interesting. For example, just yesterday we hosted a specialist in applying this to the brain. By recording the brain's electrical signals when someone looks at an image, we're starting to be able to reconstruct just from the brain the image in question. It's not perfect yet, but we can do it. But there's a much harder question. How does the brain actually work? We can do extraordinary things by observing the brain, but we don't even have the slightest idea how it works. That means we don't know how information is represented in our brain. It's a subject we couldn't even approach before. I've decided to do that in my next reincarnation. I've spent a lot of time in India, so I pretty much believe in reincarnation. At this point, it's a great topic to take up in a future reincarnation. Before, we couldn't even approach it. So AI is data, 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 and then algorithms that are all kind of the same, but we don't understand them. And the big mystery of why they work.
If we look a little into the future, should we expect to see innovations in the field of computer science? Or are these fields that have reached a ceiling?
Well, in that case, I really like Pierre Dac, who used to say, prediction is a difficult art, especially when it comes to the future. It's very hard to say. Classical computing has solved a lot of problems. For example, how much does it cost to do a calculation? Except one. Sauf un. These are what we call problems of complete independence. They're very simple. Computations with true and false values and or and not, for example. We check large formulas to see if they're true. We don't know if it's exponential or polynomial, meaning easy or hard. We don't know. It's still one of the 7 Millennium Prize problems in math. All right? And that's absolutely huge because it's useful for everything. In particular, almost all computer communication and coding protocols, what we call cryptology, is based on this. If we already know how to decode all the current codes, the ones that have been widely used for a long time, we know that a quantum computer can break them. If it's big enough and reliable enough, which is far from being the case, but that's not impossible. I've seen it. Physicists have a lot of resources. They're not stupid, and they've done a lot. So it's possible. There are already standardized candidates to replace them that are already in use, but the fact that we can't break them is still purely conjectural. The mathematical conjecture for the most widespread problem in the world, which is encrypting data. And yes, so no, that's not finished. Classical programming is always progressing. The web has changed completely. The number one language is JavaScript, which is based on lambda calculus, which I mentioned at the beginning. It's not the best design language, but it's not stupid either. We mix JavaScript now in a pretty clever way because JavaScript, when it comes to making interfaces, the way it handles events is completely messed up. So we get rid of it and do it differently. We don't get rid of it, but we hide it and do it differently. It's much simpler. So that's still changing. But obviously things in essence change faster. It's a basic law. Yes. So I don't have the expertise to talk about it. I don't like to talk about things I don't have expertise in, which isn't that common.
That's much too rare. Which is much too rare today?
Unfortunately. Yes, I think so. That is to say, I can't speak dogmatically about things like that. I'm always cautious. We always only talk about his past.
Right. We're wrapping up the interview. The book will be in the description. Thank you, Gérard, for this very interesting interview.
I think you're doing very important work. Honestly, I wish I had a lot more colleagues who thought that way. Because computer science isn't even taught in France. In high schools, for example, girls are advised to choose something else. Regularly, and in good faith, the teachers say what they think. They've never had any contact. So there's still work to do.
In any case, thank you very much for this conversation.
Thank you.